Okay, guys, so let's start with this lecture. So, today's lecture is going to be about fraud proofs. So, fraud proofs are a very important component of how optimistic rollup works. So, if you have attended the last lecture where we had explained the different, like what are basically layer twos and what are different type of layer twos, then optimistic rollups are a subclass of that and a very important component of how they work uh, are called for fraud proofs, which we are going to learn in this lecture. So let's have a quick overview of what optimistic rollups are. So optimistic rollups basically assume that the transactions that you're submitting on the rollup are valid. Uh, so that way you don't have to re-execute every single transaction. On Ethereum, when you submit a transaction, every single validator is basically checking if the transaction is correct or not, and that incurs a lot of computational cost, hence the high gas fees on layer ones. What optimistic rollups do is that you submit a transaction to the rollup, and it just submits the data of it on Ethereum, and no one re-executes the transaction, and hence you don't have to deal with all the extra competition that comes with it. But then, because of which the gas prices are very less. But then, uh, how do you then ensure that the transaction you're submitting are actually correct? So what happens is that you assume on optimistically that the transaction is correct. But if the transaction is not correct, then anyone who's observing the transaction can raise a challenge and submit what is called a fraud proof. We're going to learn what a fraud proof is, what a fraud proof is. But if a fraud proof is successful, that means that the transaction submitted on the optimistic rollup is indeed invalid. Then whoever had proposed the transaction will get slashed. So now who is the proposer? What does slashing means? And how do you check if a transaction is valid or not? We are going to learn all of this in this lecture. And rollers need to build a lot of infrastructure to make this possible. So in order to study all of this, we are going to take a case study of optimism. Optimism is a layer 2 rollup, which is, as the name suggests, is an optimistic rollup. So this is what they've done. They've created their own virtual machine and OVM, the optimistic virtual machine. They have created their own execution client called optimistic get, and then they use something called state commitments and microblocks to basically generate intermediate state commitments. And whenever you submit a transaction, it goes on to something called the canonical transaction chain, and an intermediate state is generated on the state commitments chain. And then you can use all of these components to generate fraud proofs and verify if a transaction is correct or not. So let's get into it. So as I've shared this article before, it's an article written by the CTO of Paradigm. It basically goes over in very technical detail how optimism itself works. And this lecture is going to be a rough overview of this article. So if you after this lecture want to get a more deeper understanding of how everything works, you can check this out. And you can see that the article covers a lot of different stuff like how OVM exactly works, how optimism change the Solidity compiler to make certain opcodes available, how they change the get. But we are not going to go too much into deep into that. We're just going to focus on how fraud proofs work in optimism. So in order to do that, we'll have to first understand how transactions are sequenced and batch in layer 2s. We have an entire week of lectures coming up on sequences, so we'll go into detail in those lectures. But for this lecture, let me just give you a preview of how that happens. So whenever a user submits a transaction, it is received by an entity called a sequencer. The sequencer basically batches the transactions and submits them onto something called a canonical transaction chain, and it generates a state of each of these transactions. And the users can they have an option to not use the sequencer and submit it directly to the CTC, but it comes after the delay. So let's understand it deeply through this diagram. So as you can see, there are a bunch of users here. All of these users are submitted a transaction to the sequencer. Now, as the sequencer receives the transactions, it also uh, it also basically orders them based on how early a transaction is received. And when it reaches a particular batch, a particular size, it batches all of these transactions, and it then submits it onto a CTC. Now, as you can see in this diagram, you might see that it is a blockchain, but it is not a blockchain in the traditional sense that there is a block and the block has a bunch of transactions, because optimism does not have blocks in that sense. Optimism do have blocks, but they're sort of micro blocks, because each transaction is a block in of itself. Now, why is that? That is because, as you might know, that the virtual machine of any blockchain is basically a state transition function. Now, what does that mean? It means that the blockchain has a state. A state means that, okay, this account has this balance, this contract has this storage variables which has these values. That is basically the entire state of the blockchain. When a bunch of transactions come, like when a block comes, which is a group of transactions, these transactions basically change the state of the blockchain. And then after the block is basically added to the blockchain, you have a new state of the blockchain. So that's why the virtual machine which processes these transactions are called is basically also called a state transition function. So that is how that is how Ethereum works. But if we do the same thing for optimism, there is a problem. And the problem is that we have to eventually verify if a transaction is correct or not. And if we do not have the intermediate states after each and every transaction, then let's say that a block has 1,000 transactions, and the 999th transaction is false. Then you have to execute all of the transactions before that to basically get to that transaction, which is going to be a very inefficient way to prove if a transaction is valid or not. So that's why what optimism does is it creates a block for each transaction. That way, we have a state for a state after each transaction. So we know that okay, if a transaction is invalid, then we'll have an invalid state just after the transaction. So that's what the sequencer does. It takes all of these transactions, it batches them up, and it submits it onto the CTC. And whatever state is generated after applying that transaction to the previous state, that is being put onto a separate chain called the state commitments chain, or SCC. Now, the users do not have to use the sequencer on its own, because the sequencer is a centralized entity. So the sequencer can censor your own transactions. Like you can submit a transaction to the sequencer and it can reject the transaction. So if you don't, so if your transaction is, let's say, rejected, you can directly put your transaction onto the CTC, and that happens on the first in, first out basis. So it's like a queue, right? But the transaction happens after a delay. Now, why is that? The transactions happen after a delay because, let's say, the sequencer is batching a transaction and you send a transaction in between that. So that transaction can it can have a negative an invalid state interacting with other transactions. So the sequencer basically has a grace period. Like whenever a new epoch is generated, the sequencer gets to get some time to batch the transaction and submit it on a CTC. And after that, anyone who wants to directly forcefully put a transaction into the CTC, it can do so. So that is basically an overview of how the sequencer on optimism works and how the block structure of optimism works. So now that we are armed with that knowledge, now let's look into how fraud proof exactly work. So let's say that there is a CTC with T1 to T8, and there is a state transition, and there are a bunch of states for that. And as you can see that, let's say the sequencer is a malicious sequencer, and it submits a invalid state for, let's say, the fourth transaction. So up until S3, the state is fine. But after the fourth transaction is submitted, the sequencer submits a state which is, let's say, it gives itself 10,000 bitcoins or 10,000 ETH. And that is obviously an invalid state because it has to come from somewhere with a signature, and that did not happen here. So it's an invalid state. So since it is an invalid state, every transaction that comes after it, the state that is changing, all of the upcoming states are also invalid. So now we have a problem on our hands here on the optimistic rollup. And how do we solve this problem? We solve this problem by basically having everyone watch these transactions. So the people who are looking at these transactions, they can choose to run these transactions on the state themselves. So let's say you have S3. On S3, the transaction T4 came, and now sequencer says that the S3 T4 on S3 gives something S4, but we know that the S4 is invalid because the sequencer has generated an invalid state. So if someone is watching this transaction, they can independently execute T4 on S3 and get an S3 prime. And they can see that, okay, I'm getting S3 prime. What is submitted on the SCC is S3, is S4, sorry. So that means that the sequencer has done something malicious. So what this challenger can do is now create a fraud proof, submit it to Optimism, and since the fraud proof is going to succeed, what happens is now Optimism is going to prune all of the states that comes after S3. So now all of these states are pruned, but the CTCs remain unchanged because the CTC basically has transactions, right? And these transactions come in signatures. So the optimistic chain is now going to re-execute all of these transactions on top of S3 to basically create valid states. So now let's see how how the challenger can raise a fraud proof. So in order for a challenger to raise a fraud proof, they have to basically specify two things. They have to specify the pre-state root, and then they have to specify the disputed transaction. So in our previous case, the challenger is basically going to pass in S3, which is the correct state up and just before the dispute, and it's going to send the transaction T4, which has created a disputed state. Along with that, the challenger also have to give the proof of inclusion or proof of inclusions, and it is calling basically a contract called fraud verifier, which handles all of these transactions, all of this fraud proof uh, management. So what is a proof of inclusion? So like whenever you create a state, so a state has a bunch of a lot of data. Like let's say there are thousands of addresses. So the balance of each and every address is basically part of the state. What is the value of each and every variable? All of these things are part of the state. So you cannot have, like, if you have a block header, you have to put the information of the state in the block header, but you cannot put all of those information. So what you do is that you feed all of this information into a Merkle tree, and you submit the state root of that Merkle tree, right? So when you have to specify that, okay, I'm submitting a particular state, you'll also have to pass in a proof that, okay, this root, this state was part of the Merkle tree, and you do that by basically passing in a Merkle root that says that, okay, this root is included in this tree. So you have to do that with the transaction and with the pre-state root. Now, when you pass this data to the fraud verifier, the fraud verifier basically deploys two new contracts. It deploys a contract called state transitioner, and it deploys a contract called state manager. And these are going to be unique to the particular fraud proof that you're submitting. Now, the state manager is basically a contract which has all of the data, that is all of the context or background data that you need in order to run the fraud proof. Now, what do I mean by that? So like, let's say that you submitted a transaction T4, and the sequencer generated a malicious state for that. Now that happened on a particular timestamp, and the challenger basically raised a fraud proof on a timestamp which is like 1 hour after that. So if you want to re-execute that transaction on Ethereum, then the timestamp is going to be different, and hence the actual state that is being generated might not be the state that should have been happened. So there's a problem there. So that's why when you're executing a fraud proof, you cannot execute it straight away on Ethereum. You have to execute it on a sandbox environment, an environment which has all of the background context and all the background data that was there originally when the transaction was run on the optimistic chain. So all of this data is stored in the state manager. So now, uh, yeah. So Optimism basically creates a sandbox environment that guarantees that the execution of the smart contract is going to be deterministic between L1 and L2. Sorry, there's a typo on the slides. And as I said, that Optimism basically had to create their own infrastructure to make this happen. So they cannot use the EVM on its own, because if you call, let's say, the timestamp on the EVM, it's going to return the default timestamp, which is at that time. You do not want that. So you need to alter some of the EVM opcodes so that the fraud proofs can run. And for that, the Optimism basically created an OVM. And they basically, whenever you run a smart contract on OVM, it checks that all of the opcodes are basically optimized OVM safe or not, right? And so there is another contract called the execution manager. This contract is responsible for executing the fraud proof on Ethereum. And it basically inputs all of the OVM opcodes and it runs them on Ethereum to check if the fraud proof was correct or not. And the Optimism also modified Geth to make it OVM friendly. So Geth is basically a execution client for Ethereum. It is the most popular execution client for Ethereum. It was written in Go and developed by the Ethereum team. So it Geth normally takes messages and it sends it to whatever the message says, like whoever you have to send it to. But Optimism changed it so that whatever message you submit to Optimism, it has to go to the sequencer's entry point. And Optimism also created the sandbox environment inside of Geth so that whenever a fraud proof is generated, the execution manager gets to run the transaction instead of the actual chain. And whatever the message's original data was, like the address it was sent to, the address it is coming from, all of these are passed in as arguments. Because like whenever you settle a layer 2 transaction on layer 1, the transaction is being the data of the transaction is being sent to Ethereum through call data. So like call data has all of the arguments. When you will send a transaction from L2 to L1. This is a topic that is related to something called data availability, and we might have a lecture on that as well. So I'll not go too deep into that. Now, OVM maintains an order list of all the transactions, and as I said that each transaction is a block. But then if you know that Ethereum in a block has a block gas limit. So you cannot have more than a certain amount of blocks on Ethereum. So we also need to have some sort of rate limiting factor on Optimism as well. So what Optimism has created for that is called an epoch. So an epoch is basically an interval of time. And Optimism has defined that, okay, a particular epoch can only have a particular amount of gas consumed in that. So if you have submitted a transaction in an epoch which has exhausted gas, it basically returns that your transaction is too early, and you can resend it after the next epoch starts. So now let's come back to the fraud proof. So as you said that the pre-state is loaded into the sandbox environment. The pre-state is basically S3 and it is loaded into the environment. And the challenger triggers a function called the apply transaction, which invokes the run function on the execution manager. The execution manager, as I said, was responsible for executing this transaction in the sandbox environment. And basically, what execution manager returns is S4 prime. Okay, S4 prime is the actual correct state that should have been generated. And now what Optimism does is basically it checks that if there is a mismatch between the state that the execution manager has returned to us and the state that the sequencer had submitted on the state commitment chain. And if there is a mismatch between the states, then uh, yeah. So as I said that there is the finalized fraud verification function is called, which actually checks if there is a mismatch between the state roots. And if there is a state root mismatch, that means that, okay, the fraud proof is successful. The state that was submitted by the sequencer on transaction 4 was indeed invalid. And then all the states after that must be pruned and re-executed to obtain the correct states. Now, you might have a few questions as to like what if someone spams fraud proofs and what if the sequencer itself spams a lot of states so that in the hopes that, okay, at least one of the state is not checked so that an invalid state is passed. So in order to mitigate all of this, basically Optimism runs on a proof of stake network, a proof of stake mechanism. So the sequencer or any other party, basically any party can submit transactions, can submit the state on the state commitment chain. But in order to do so, they have to first put some amount as a stake, right? So this avoids spamming, first of all, because not everyone can do it. And then once someone has put a stake on it, if they submit an invalid state, then their stake will be slashed. What that means is that, let's say you deposit some money and you're submitting states onto the SCC and you have submitted an invalid state to get some reward. Now, a fraud proof have been generated for your invalid state and it is successful. If it's successful, then the money that you have deposited to the optimism contract, it will be taken away from you. So that is basically an incentive for you not to provide invalid states. Is that I think that's clear to everyone. And then you might ask that, okay, what incentive do people have to check if the transaction is correct or not, right? So what happens when the stake is slashed is that a percentage of the stake is burned away, and the remaining part of the stake, it gets redistributed uh, to the entities that basically raised the challenge and provided the data for fraud proofs. So this incentivizes everyone to check each transaction, because let's say if you're checking a transaction with optimism and you find an invalid state, then if you submit a fraud proof and you know it's going to verify, then you're going to receive a reward. So you'll have an incentive to do that. And that is basically how fraud proofs work, and that is basically how optimistic rollups also work. So are there any questions so far? Okay, so if there are not any questions, then that is it for this lecture. And yeah, that was it for the lecture. Thank you.